Hey, good morning, everyone. Welcome to the Common Good Podcast. Doug Pagitt here in Minneapolis, Minnesota, joined on Friday, because it's Science Day around here, with astrophysicist, pastor, professor, murder, Paul Wallace. And hey, I'm glad to be back, Paul, because I've been away for what was supposed to be like 1 week and turned into a couple of extra days. I went off to Mexico and was welcomed into the country, by the way, just welcomed in graciously. Allowed to come as a visitor, and then was allowed to leave. Something we should do with Mexicans in this country, I would say. Very good. But I had a great time there, and glad to be back, and excited to talk to you. I'm in Minneapolis, where we're about to get a sleety, stormy, wet, sloppy, dangerous.
Really?
Yes. So I'm not one to complain.
I should turn my camera to my window. It's going to be about 74 today and totally clear. It feels like April.
That's in Decatur, Georgia. Hey, right. We're not here just to talk about, the lovely beaches of Mexico or the beautiful sunshine in Georgia, but rather what happens in the cosmos. And we're going to do a abbreviated show today. But this great article came up, Paul, and you were the first person I thought of, and I thought this is what we're going to talk about because, you're the only one I know personally who really understands any of this stuff. So thanks for helping all of us.
Sure thing.
And it was this article that's I have a little in my news feed. I have a special science and astronomy section, and this article says 7 questions about the expansion of the universe. And I got to tell you, I have all 7 of these. Some of these questions I didn't even realize should have been a question until I read them.
Yeah.
Pretty cool. All right. So I know you've had a chance to look at these. Shall we dive right into the beauty of the cosmos?
Sure.
All right. And hey, part of the reason this really matters is that the United States and Russia and many others around the globe joined together in sending cosmonauts, astronauts, and I don't know, whatever other knots up into the space station and share all that. And so with the violence that's coming out of the Putin choice of Russia to attack Ukraine, all of this is up in the air, literally and metaphorically.
Wow.
So it's a messy thing. But anyway, we will, with that in mind, and hoping that people can figure out how to keep a space station going when you have a bully of a partner in the space station. Let's talk about what's going on up in the skies. All right. So Paul, the question number 1 that's raised in this article, which I thought was really good, is this idea of the cosmos is infinite, right? There's no boundary to it. There's no edge of which things inside, sort of, I guess. But this question says, so if it's infinite, how can it be expanding? And apparently when you all as astrophysicists and cosmologists talk about the universe is expanding, you mean something really specific that might not meet all of our kind of imaginations.
Right. That's right. So the question, if the universe is infinite, how can it be expanding? Well, first off, we don't know if it's infinite or not. I myself prefer for it not to be infinite.
Come on. I thought that was one of the settled. Oh my gosh. Okay, that's beautiful. All right.
We don't know if it's infinite or not. We know that we can't see all of it, but we don't know if it's infinite or not.
Okay, talk me. And we may not even get beyond this one now today. What you prefer that it's not? I had assumed that was one of the givens.
No.
What's the other option to the universe being infinite?
Well, it could be finite, but still without bound. Does that make okay? Okay. So think about suppose you are Doug. Suppose you and dear listener, suppose that you were sort of 2-dimensional. You're kind of flat. Okay, you just live in 2 dimensions. Okay. But you don't occupy like a flat surface like a tabletop, but you occupy like the surface of a ball.
Okay.
So that space is finite because there's only so much area on the ball, right? But it's not bounded. It's not like there's a place where you're going to go fall off the edge, right? You're stuck to the surface of the thing. So in this model, it would be a situation where if we could sort of stop the expansion of the universe and then go in one direction, we'd end back up where we started.
I see. Okay. All right.
Like the surface of a ball. You'd end up, if you could go far enough, travel far enough, you'd end up right back where you started.
And if is that the description for a non-finite universe?
Yes. Or right. It's non-finite. It's finite but unbounded.
Wow. Okay, that's a great.
Did you follow me? Yeah.
Yeah. That's a beautiful distinction. All right. So you said you would prefer that it's not infinite.
Yeah. I think in physics, we really try to avoid infinities in general. And that just seems like I've got questions for truly highly trained cosmologists if the universe is infinite. I'm not sure where I don't know, an infinite amount of matter in space. That just doesn't compute for me.
So this is where an astrophysicist and a cosmologist might be are in different.
Yeah, I'm just not highly specialized and trained in cosmology. I'm talking about somebody who might be a cosmologist at MIT or something. Somebody who really spends their has devoted 50 years of their life to this very topic. Wow. Not somebody like me who knows knows enough to teach a college class, undergraduate class on it, but is not truly a specialist.
So being an astrophysicist does not make you, as you are, does not make you a cosmologist by training.
Yeah. Let's just say there's a lot of people out there who know a whole lot more than I do.
Okay. All right. Fair enough. I know that feeling. And I know that feeling. There's a whole lot of people that know a lot more than you do about this topic. When you read a headline then that's in this from the BBC in this article that says, if the universe is infinite, starts with that as the premise and then asks the question, how can it be expanding? What goes through your mind? Do you think like, well I don't know,
I mean,
doesn't need to be infinite.
I can allow that it can be infinite. If it turns out to be infinite, that's fine. And I think I understand the question. I haven't actually addressed the question yet. I think what the question is asking is this. I think in the popular mind, the idea of the expansion of the universe is that there's all this empty space out there into which the universe is expanding. Like an explosion, it's like all this space is already sort of sitting there waiting, and then this bomb goes off right in the middle of it, and there's a sort of a shock wave that goes out, and in front of the shock wave there's empty space, and behind the shock wave there's all the bomb stuff, right? It doesn't work that way. There's not all this empty space out there waiting to be filled up by the universe and by galaxies. So the question, if the universe is infinite, how can it be expanding? To me implies that's the image that people have, is that you can't have an infinite universe expanding into this empty space that's waiting for it, else it wouldn't be infinite. Right. That's the problem.
That's totally the image I had in my head and was trying to wrap my thoughts.
But the way that we astrophysicists understand it is that the space itself was wrapped up in the Big Bang. In other words, space itself is part of the creation that occurred at the Big Bang. Space was not sitting around waiting for a Big Bang to happen in it. Space was wrapped up inside the singularity we call the Big Bang. And the expansion of the stuff, the moving away of galaxies from each other is occurring because the space itself is stretching out between them.
Wow. Okay. Say that one again.
Okay. It's like this. Here, I'll give you an image. Okay. Imagine that you've got a big like gym floor with all these people standing on it. Okay. The gym floor is kind of like the space, and the people are kind of like the galaxies. Okay. You can imagine these people moving away from each other and expanding in two ways. One is they could all run away from each other. Like
so they go social distance. Yeah. Right.
Across the floor. That would be like a galaxy moving through space. You could also imagine that the floor itself is expanding. carrying all the people away from each other.
Great. Hey, so I've got in my mind here, we blew up these big balloons for our grandson, like 12, 15, 16 inches. If I were to put little dots on that balloon while it's laying flat on my table, they would be so close to each other. And then as I inflate the balloon and the balloon stretches, the dots get further apart. Is that what you're describing?
That's exactly right.
Huh.
And that's exactly right. But the difference between the people on the floor of the gym and the dots on the balloons is the people on the floor can walk around. We can move through space.
I see.
Okay. And galaxies can move through space. But the expansion of the universe is more like your balloon and more like, in my analogy, the floor actually itself expanding and carrying all the people away from each other.
Wow. Okay.
Yeah.
Now I'm still stuck, I guess, with Toy Story and To Infinity and Beyond in my head. So I think I'm locked in as an infinity guy. All right. How fast then is the universe expanding was the next question that came from this. I found this one very interesting. So if it is expanding, how fast? And then I guess kind of why does that part matter?
Well, it matters because it has to do with the age of the universe. How old it is, because if it's expanding very rapidly, that means the universe is younger. If it's expanding very slowly, that means the universe is older. It took longer for it to get to the point where it is today. So you might, if you read up on this stuff at all, if you, even in this article right here, they mentioned something called the Hubble constant, which tells us how fast space is expanding. And basically it has you imagine two galaxies that are about 3 million light years apart from each other. Okay. About 3 million light years from each other. Those two galaxies would be moving away from each other at about 75 kilometers per second. So that's about 50 miles per second. So two galaxies, 3 million light years away, would be moving apart from each other about 50 miles per second. Which is pretty fast for us here on Earth, right? 50 miles per second. But in the land of the universe, that's not particularly fast. So that's how we measure it.
Okay. Yeah. And I mean, I guess just thinking about the reality that everything is moving, right? Like space is moving, the universe is like, because it's easy to consider that things that we see and know are settled and stable and observable and are now as they were then. Well, the reality is nothing is that way. Anything that exists, atoms, molecules, space itself, it's moving. I posted this little National Geographic story about how the continents have moved over the some billions of years on the Earth, and how parts of what are now separated by oceans were connected to each other because of the tectonic plates. And in this article, it just says, oh, and by the way, like our North America is moving like 3 feet a year or something. Like there's some little amount of shift happening of the entire thing. That and this conversation, I don't know, it just kind of reframes the human experience that things feel so settled or constant. And
it when you step back and think about it, it's a little mind-boggling what you're talking about. I'm sure there was the same sort of sense of almost like vertigo that struck people back several hundred years ago when they realized that the Earth was moving around the sun. Because I mean, that itself is enough to throw you off.
That's right. And just the fact that the Earth is rotating itself and none of us feel it, you just got to stop and remind yourself of that, and that's not what we feel when we feel wind, right? That we're not on a merry-go-round.
Exactly. In fact, that was one of the arguments actually against a moving Earth. People thought if the Earth was rotating so fast, wouldn't there be this like, constant wind?
That's right. Always in the same direction. All right.
Yeah,
so,
right.
So the universe is expanding. Does that mean, and this is the third question, was it ever expanding at zero rate? Like, was there
Not that we know of. No. If it did, it was before the Big Bang, and that's kind of off limits to us. Certainly ever since the Big Bang, 13.8 billion, give or take a couple 100 million years ago. Ever since then, it's been not non-zero. If it was ever zero, it was before the Big Bang, and there's kind of like a wall in time. We really can't access, before that moment. We can't see. It's really like having a wall we can't go over or around. We're kind of limited.
Okay, I guess that's a good point, that these things we've been talking about, this knowledge that we possess about this, comes from some kind of observation.
Absolutely.
Not just from theoretical suppositions. Everything I've said
is based solidly on observations. Yep. We're not just making it up.
So how long have we known this then? If it's based on observation, we're talking like in the last 50 years.
What about the Big Bang generally?
Yeah, the expansion of an infinite or non-infinite universe.
The Big Bang was first suggested in the late 20s, early 30s, so a little under 100 years.
Okay.
Before that, it was assumed that the universe was basically infinitely old. Most scientists assumed it was infinitely old. And Einstein himself he assumed it was infinitely old. When he first solved his equations of relativity, he did not allow for a Big Bang. It was actually a French priest Belgian priest who first suggested a Big Bang, said that Einstein's equations were consistent with what today call the Big Bang. That was the late 20s.
And wasn't that, now I'm remembering this from a book that I read, wasn't the Big Bang sort of used as a derogatory term for this notion?
Yeah, it was a fellow named Fred Hoyle who hated the idea. He hated it largely because of, several reasons, but one of the major reasons is he didn't like the idea because it suggested sort of a Genesis 1 kind of thing. The religious feeling of it he did not like, and he coined it on, I think it was a radio, maybe a BBC radio program. He coined it. He was being interviewed and he coined it. He was an astronomer who believed in what was called the steady state theory, which was that basically the density of the universe doesn't change over time. It's basically infinitely old. He didn't like the idea of a beginning because it's felt to him too religious, too much in line with the religious narrative. And he used the phrase Big Bang to deride it, to mock it. But as so often happens, those names, those mocking names, are adopted by the people who
All right, so if the universe is expanding, does that mean that the mass, the amount of what there is also increased? Because one of the assumptions that I've had going into this, and the article also has, is that energy can't be created or destroyed, only converted. But I've been reading some other things where they say maybe some things do go out of existence, but generally, or maybe always, things there isn't any more or any less of anything than there was always or at the beginning. We're just rearranging it. Is that all right? And if so, what about the mass of increase?
That's an interesting question. Certainly what you say, you talked about energy being converted into mass and energy are convertible into each other. In other words, you can have two particles and have them disappear from the face of the universe, have that mass be gone completely. It can be converted into light, into energy. That can happen. And you can go the other way too. You can convert light into mass. So that total sum of energy plus mass has not changed.
Okay.
But at the beginning, at the very beginning, everything was light. Matter, the phrase that's used, mass condensed out of light, out of energy. And so the total sum of mass and energy has not changed, but at the first moment of the Big Bang, everything was light and there was no mass.
So at the end of all the expanding, whatever this is what happens? Is it that all the mass then returns to energy, and soon the universe will be nothing?
That would happen if that would happen if the universe reversed itself, if it fell back on itself. If it instead of expanding, it started to contract. As it got hotter and hotter and hotter, it would be converted more and more back into light, into energy. But for the most part, the universe's mass has not increased it ever since the first few, I don't know, I guess maybe the first couple 100,000 years of the universe's lifetime. Ever since then, it's been roughly the same amount of mass.
So some, I don't know, tens of billions of years ago, it's remained relatively stable.
Yeah. Over the last 10 billion
years. Why is that? Is it because the Big Bang was the only it took that kind of event to change so much energy into mass? Is that why?
No, the energy changed into mass shortly after the Big Bang. The Big Bang just produced a whole bunch of light, photons we call them, and that light condensed into matter pretty rapidly afterwards, and the overall amount of matter has more or less stayed the same. So it was a radiation dominated, we call it a radiation dominated universe, a light dominated universe at the beginning, but now there's more matter, and roughly the amount of mass in the universe at this point is not changing anymore.
Why did it change from radiation and light and energy into mass then and not happening now?
Because it got cooler and less dense. That's basically the answer.
The expansion caused that to happen.
Yeah, that's right.
Huh.
Weird but true. Now, what can happen sometimes is you can have, imagine, if you will, what we would call perfect vacuum, like just nothing, it's hard to imagine, but it's empty space, right? Just empty space.
Okay.
One thing that does happen is what we call virtual particles do in fact exist in that vacuum. There is no such thing as a vacuum, a true vacuum, a truly empty space. Even in what we call perfect vacuum, science, we call it quantum mechanics, has demonstrated to us, and it's been shown experimentally to be true, that pairs of particles do appear out of the vacuum and then disappear rapidly again. That does happen, but that doesn't last more than very, 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 very short time. Weird but true. So they're popping in and out of existence, basically, even within a vacuum.
Like that's something that's known enough that you and I can sit here and talk about it and can reference a test.
Yeah. You can look up something called the Cashmere Effect, and it was basically the experiment that showed that demonstrated that this was true.
The Cashmere Effect.
Casimir, Cashmere Effect. It was predicted. It was predicted theoretically before it was experimentally verified.
That just has a nice ring to it. It sounds like something that they would have offered at the resort we were at on the vacation. Like, are you interested in the Cashmere Effect? Because if you are, there's a
please, I'll have two.
Well, yeah, over here. So I'm just thinking, when now we can talk about this. There's a name for it. There was a theory, and then an experiment, and then it's understood enough. When people are first experiencing this, like particles are popping into existence and then popping out of existence, like that must have struck their minds as like, was something wrong here. This can't possibly be happening. There must be a moment of disbelief of what they're witnessing.
I'm sure, but I'm not sure if it was Casimir who predicted this to happen, or it was Casimir who experimentally verified it. But I suspect that by the time this was predicted, they were pretty sure that it was real. Because I suspect by the time it was predicted, I'm not sure what the date was, that quantum mechanics had been successful enough to where they were like, if all these other things are true, then this must also be true. I don't know the story though. I like to know the story on that one, but I don't know.
Yeah. And I'm just thinking about what of those theoretical notions are happening to to people right now, to the young scientist who's, I don't know, 24 and is like, I'm telling you, this thing has to happen. And everybody else around her is saying like, no, that's not how this is going to go. That's not how this works. She's like, I'm going to prove it. And then I don't know, in 50 years, she's going to win some international prize.
Right.
Like whatever
posthumously, right? Like after they die, that'll be shown to be true. That actually has happened a lot in physics, where theory has predicted something. You know, somebody sat down at a blackboard or a piece of paper and scribbled out some equations and predicted something, and it turned out to be right. That has happened. I can think of 3 or 4 or 5 cases right off the top of my head. Famous ones, not even ones that aren't so famous.
Yeah. And those people must live with just people, others in their field, I don't know, mocking them, tormenting them.
At times, at times.
Wrong. I mean, someone has a vested interest in whatever the known knowledge is. And is not going to be happy with whatever the new knowledge is. All right. So back to these questions. This one was, I didn't even know this could be a question. You know, it's like when you go to, I don't know, graduate school or college, or I guess, you know, any education, and the point is to learn new questions, not to learn answers.
That's right. That's right.
This is one of those. If the universe is 13.8 billion years old, how is it 92 billion? How is it that the universe is 92 billion light years across? Now, there's a question that the smart kid knows how to ask in the back of the classroom.
Well, so the problem is this: the universe is 13.8 billion years old, but we can see objects that are further away than that now. So the question is, if the universe is older than 13.8 billion years, how can we see things that are further away than 13.8 billion light years? The light shouldn't have gotten to us. How can the observable universe be 92 billion light years across? And the point here, what's behind this question is that the speed of light is considered sort of like the speed limit of the universe, right? You can't go faster than that.
Yes, it's another one of the settled assumptions that I had at the start of our conversation today, which fearful is about to go away.
I would like to take you back now to my analogy of the people on the floor of the gym. Okay. There are 2 things that can move, right? The floor itself can expand, and the people can also walk across it.
Okay.
Right. So it's an expandable floor. And if the floor expands, people will be spread out from each other. They'll be getting further and further away from each other, but they can also walk across the floor. The speed limit applies to how fast the people can walk across the floor. Not to how fast the floor can expand. The floor can expand as arbitrarily fast.
Because it's not energy or matter.
Right. So exactly.
It is what? What is the universe that is expanding? It's not energy or matter.
That's a good question.
What is it?
That's a good question. That's one of those questions that as far as my physics knowledge goes, has never directly been addressed. It's one of these things. It was sort of these starting assumptions that you have that space is a thing, and we all kind of know what it is. You know, turns out we don't really know what it is, but we still haven't quite gotten to what space is. But the point is that space does not. The space itself does not have that limit on it.
Okay.
And so early in the universe's lifetime, the floor expanded far faster than the speed of light. And so it allowed for us to have and I should say also at the end, that 92 billion light years across, it should say that's just how much of the universe we can see. That's not the whole universe.
Oh, wow.
That's just how much of it we can see. Kind of like being out on an ocean in a boat in the middle of the Pacific. You can only see, like, you know, if you're standing if you're standing up, you're 6 feet tall, you're standing up in a little boat, in a little like rowboat, you can see 3 miles in every direction. That's it. There's more beyond that. That's all right. Before the curve of the earth drops away from you and you can't see over it. You can't see beyond it. That's kind of how the universe is. We have a little circle that we can see. Of course, it's 3-dimensional, not 2-dimensional, but There's a certain distance that we can see, and beyond that, because of the geometry of the problem, we just can't see beyond it. So that 92 billion light years across is our little patch of universe that we can see.
So if this question if the universe is 13.8 billion years old, how is it 92 billion light years across? Is the smart kid question, the question that's asked at 10 a.m. in the astrophysics class. The what is the universe made of is the other college kids asking that question at 3 a.m. on a Saturday.
That's right. After having a few cold ones. Yeah.
Staring up at the sky. What is the universe, man? It's not energy or matter or all the rest of it. And they're, I don't know, they're kind of both interesting types of questions, it seems to me.
I'm basically stuck where that second kid is my entire life. I'm like, what the hell?
Well, totally. I mean, this has been the hard thing for me about the expanding universe. It describes something. There's a thing that's expanding, but that thing is not any of the other elements that we talk about when we talk about things. It's just.
And on that level, I don't know what space is either. Somebody may have a more clear view of it than me, but on that level, I don't know what space is either. I can measure it, I can talk about it, but.
Well, this is where the religious elements of, as religious people who also speak of spirituality, God, whatever, are also sort of in the same dilemma, right? There's just things that are not, I don't know, that feel as if the descriptions we have for the way of the reality don't fit the same descriptions that fit most other things in the reality. Something is different.
Yeah, and I feel that way about virtually everything. I mean, we can talk about space-time and we can have our equations, Einstein's equations and all this, and we can do our four-dimensional tensors and all this stuff, and it's beautiful and it works and it really describes something real. But at the end of the day, I'm like, it's like there's something essential about the reality that goes right through that, like a sieve. It's like what is this miss? It's missing something, and that's where, and it's not in the areas that we don't know. For me, like a lot of people sort of put God in these areas, like before the Big Bang, or like, or consciousness or something like that, someplace that we don't know. But I don't think of God that way. I think that there's a fundamental, and I hate to use the word mystery because it's so hackneyed, it's so overused. But I feel like that even in the stuff where we think we know everything, I still think that there's something that's missed by science, something essential that kind of passes through that filter and gets lost.
Yeah, I'm with you. And that's such an interesting notion, that little line you just said there, that there's these persistent questions, wonderings, struggles with how things are, not generated by what we don't know, but generated by the things that we do know. Like once you know something, then it creates another thing you can't understand.
And it feels bottomless. It feels like, I've heard some scientists say that we're going to find a theory of everything and then we'll know everything, but I don't, I'm skeptical. I don't know how useful an idea that is.
Well, I think Ryan Phipps, who I know made a comment here in the chats, is going to could easily make a comment about Buddhist thought, saying that the more one gains knowledge, the more the mysteries start to open up to you, right? That the knowledge is not to remove wonder.
Right.
It's to create more access to new wonderings.
Right. It compounds it. Yeah.
Yeah. There's Ryan Phipps right there. All right.
Thanks, Ryan.
Is the expansion of the universe speeding up? So this expanding gym floor metaphor, is that constant rate, speeding up, slowing down? Where do we think we are? As we've been looking at the 13 billion year old universe for the last 50 years. What do we think? How do we judge the universe? Is it speeding up, slowing down? What's it doing?
Well, for decades, we assumed it would be slowing down for decades, all through the 20th century, pretty much from the time the Big Bang was proposed And as the evidence for it came in, over the decades, everybody assumed it would be slowing down because gravity is attractive. Gravity is always attractive. We have all these galaxies attracting each other. So we thought that would be putting the brakes on the expansion. But it turns out in 1999, a couple of different research groups did independent work and came to the same conclusion, which is the universe is speeding up.
Wow.
It's going faster and faster every day. And so there we are. And we don't know why. They use the term dark energy to describe this effect, and they attribute it to something called dark energy, but the very term itself indicates that we don't know what it is. It's dark. We don't know. That's the term for, not knowing.
Yeah.
So we don't know, but we do know that it's speeding up faster every day. Weird but true.
Weird but true. All right. So one last part that's weird but true. If the universe is expanding, this is another smart question that I don't really understand. Is getting to distant planets possible? I guess it's sort of asking if the floor is moving apart so fast, can the people get to the point where the people just couldn't get to each other anymore?
Yes. If we're talking about planets in other galaxies.
Okay.
But if we're talking about planets in our own galaxy, the expansion of the universe is not making our galaxy expand.
Okay, hold on a minute. All right. So
our galaxy is not expanding with the universe.
So if our galaxy is one of these people on the gym floor,
right? The people themselves are not getting bigger and swelling as the floor expands.
Why is that? How come
because
all
they're
things...
held together? Because the people are held together by electric forces, and the galaxy is held together by gravitational forces.
All right,
so the galaxy is holding itself together. In other words, the galaxy, you can think of the galaxy as a single. If you think of your own body, right? Your own body is a single thing. It's held together, but obviously it's made up of little atoms and stuff, right? Well, those atoms are held together by electric forces. That's why we're stuck together. That's why if we turned off all the electric forces in the universe, our bodies would just fly apart.
Okay.
So we're held together by electric forces. Galaxies are single objects like us, but they're held together by gravitational forces. In either case, as space expands, our bodies maintain their integrity and the galaxy maintains its integrity, and they stay held together by their own forces.
Huh.
So our galaxy is not getting bigger as the universe expands. So our meter sticks are not getting longer.
Okay.
Right.
Well, okay.
And how would we know if they were, right? If everything was getting, I mean, that's a fun thing to think about. But the point is that they're not getting longer. The galaxy's not getting bigger. So if we're talking about visiting planets in our own galaxy, the expansion of the universe does not affect that. It's going to be hard no matter how we do it.
Wow. So whatever forces are causing the expansion of the indescribable universe, whatever those forces are, they are either not powerful enough to overcome the gravitational forces of our galaxy or something else. That seems curious that they're not as strong as gravity in a galaxy, like that the universe itself is speeding up and expanding, whatever number you said earlier, seems 50 something, seems really fast, but that's not having an impact on the other things that are also existing in space because the forces of gravity are strong enough.
Right.
That's
Things
right.
are close enough to each other that the forces of gravity are strong enough. Yep.
That feels like a metaphor for other things. Like if we just stay close enough to each other, then that will overcome gravity that wants to tear us apart. That seems like the kind of thing you can preach.
Life lessons from cosmology.
Yeah, that's right. A science sermon could come right out of that one. Paul, I love this so much. It's so helpful. Peggy asked this question, which if you have one more minute, I think would just be worth it because she says, how much protection is given to the Earth by the other planets in our solar system? I guess what I'm asking is Are there planets that are hit more often by things in the air with more damage? Like, should we colonize Mars if we get bombarded by asteroids? So
that's a good question.
Yeah.
Yes, we are. We have Jupiter to thank for that, for the most part. Jupiter is hugely massive and orbits outside the sun, and has done a pretty good job not keeping the inner solar system completely clear of damaging asteroids and so forth and comets, but definitely helps out. Definitely helps in our favor. So Jupiter does, in fact, protect, in some senses, protects the inner solar system by attracting comets and asteroids and so forth. And we've seen comets strike Jupiter's surface. We have films of it. Mars is a little further out, a little closer to the asteroid belt, probably a little more dangerous in that sense on Mars. But not so much that it's going to keep Mr. Musk from getting us there.
Then get hit by an asteroid. Be perfect. Hey, Paul,
we established the first colony on Mars 100 years from now, and
wham,
a month later,
and Alanis Morissette song starts playing right in the background, right as that happens. Just a little too ironic. Hey, what do you're a college professor, you teach on Fridays. What are the good students going to learn today?
Optics. We're doing mirrors, spherical mirrors, like your makeup mirror, you get your face real close to it, your face looks huge.
Yeah.
Have you ever tried to step back from one of those and see what you look like from a long way away? Do you know what you look like?
Oh, my bathroom's not big enough.
Yeah, maybe not. But, you get up super close to it and your face is so big, you can count your pores, right?
Yeah, right.
But if you step back from it by 3 or 4 or 5, 8 feet or something, you'll see yourself really small and upside down.
Well, this has been fun. And you're going to talk about what's going on with light waves when that's happening. Is that what causes that?
That's right. Light rays. We think of light more as a ray in this case than a wave, but yes, we're talking about light and why mirrors do that, or why objects actually do look closer than why objects are closer than they appear on your passenger side rear view mirror.
A little tip of the hat to Meatloaf. Thank you, Meatloaf.
That's what we're doing today.
All right. I've just written down the sentence that we will talk about some other time, that in this case, we talk about light as rays more than waves. And that feels like an entire, I didn't ever think of the difference between a light ray and a light wave. So, all right.
Happy to talk about it.
All right. I know you got to run. Sorry to keep you a couple extra minutes. See you.
No trouble. No trouble. It was fun.
All right. Goodbye, Paul.
See ya.
Hey, everybody. Glad to just a couple of notes. In the next few weeks, we are going to be, sorry, Dan, I didn't tell you we're going to do this. I don't know how you're going to fix this unless I'm just going to keep a shadowy character around the side, which seems fine. Insert yourself, friends, into that other, this little empty spot right over there. We're going to be traveling the country talking about the need for common good immigration. So if you don't already keep up on the Vote Common Good email, sign up for it. Go to votecommongood.com. You'll find out through the email and then through also what's on the website, where we're going to be in Pittsburgh and in Columbus, Ohio, in Holland, in Grand Rapids, Michigan, in South Bend, Indiana, in Madison, Wisconsin, and Minneapolis, Minnesota, at the end of March 19th through the 27th. We'd love to have you join us at any of those events and share the story of what we're up to. So just want to tap you into that. And over the next few weeks, you're going to hear a whole lot about that. So, Dan, that was pretty good today, don't you think?
Great stuff. Yeah, loved it.
I don't know why. Sometimes the weight of the world is just relieved a little bit by thinking about other things. For someone I know for some people, they're like, man, when you guys talk about that physics stuff, and it just, my mind, it just feels heavy on my brain. I'm like, oh boy, it's the opposite for me. When I think about human behavior, that feels heavy. When I think about cool, light waves and rays and expanding.
I've got to pick up the pieces of my brain that have broken into a million pieces.
Yeah. I mean, this idea that it's expanding, but the galaxy isn't expanding, just still rocks my I don't know.
Yeah,
It feels. I'm reading this book called, I think it's A Short History of Nearly Everything, or A Brief History of Nearly Everything, and it's the history of science, sort of told in like from the early 2000s, kind of the history, or biographies of science, and you just continuously met by these notions that 100 years ago, 150 years ago, we were just totally either wrong about that. Now we've been corrected, or had no idea that they existed. And matter and whatever the makeup of the universe, that feels like one of those that at some point, somewhere along the line, children, grandchildren, great grandchildren of the people that can listen to this right now are going to look back and say, and they didn't even know X.
Like, how far off are we still on some of this stuff? What are we missing, and what is just going to be comically wrong in the future?
Yeah. In fact, this book had a great comment. It said, we know more about the expansion of the universe and the origins of the universe than we know about what's 3 miles down in our own oceans.
Yeah.
Like, turns out we don't know much about how our planet is organized. The things we knew 100 years ago, 50 years ago have been replaced by new knowledge. And so all those little pictures that we have of, the earth and the crust and the mantle and the core and all that are just real dreamy little artist renditions. So
and we don't even know what we don't know.
Don't even know it. Yep. I don't know much, but I know I love you. And that may be all we need to know.
All I need to know. Yeah.
All right. Well, nice seeing you again. And thanks everybody for listening in. I don't know. Should we run through some comments? Just doesn't seem to be a lot here today. Ryan Phipps, I love this conversation. Gerald has a good one. There are degrees of infinity because limits require them to be calculated. That's an interesting thought. We'll raise that with the astrophysicist. And Gerald also seems to know a lot about this because he says there's also infinity to the plus or minus infinity power.
Yeah. Wow. Okay.
Yeah, I don't know anything about this, but that feels like a workaround. Like somebody's just put in a thing to. Like how our calendars have to be adjusted with a leap year or something, and kind of get back on track. Like
infinity to the infinite power. I remember like back in high school math, hearing phrases like that and being like, that just doesn't even seem real.
Right. And I still feel that. Isn't it funny? Yeah, I still feel that way. And then Clara asks, where are you from? Don't know what that means. And
she was apparently asking Gerald because Gerald responded Earth. They're just having their own little conversation there.
It's about to take care of it. Okay. And then, this is a good one. Tet. Want to become famous? Buy followers, Prime and viewers on your follows.com.
Yeah. So if anyone is curious how to get followers, just follow.
Where did that one come from? Was that from
Twitch?
YouTube? Twitch,
because we're streaming on Twitch.
We stream on Twitch. I mean,
we're everywhere.
Have you gone over to Twitch yet? By the way, Dan, have you ventured over?
I've never been.
I am telling you, when you shut this off, if you don't have to run to the to the care room in your house, just go to Twitch. Something Twitch. It's not Twitch. Something. Just type Twitch, TWITC, into Google, and go on and start looking through all the live streams. There's a lot of gamers.
Yep.
But the tens of thousands of people at a time who are watching live streaming, conversations like this, people playing games, who knows what else, all kinds of things being live streamed, and tens of thousands of people, less how many current viewers there are. It's bonkers all over the world. So
it's a wild time to be alive.
It's really something. And a wild time to be alive. And then Jim Eaton says, interesting. And thank you, Jim. I think he's specifically referencing that particular comment about we were talking about right at the end because I saw that one pop up. but I don't remember what the comment was. All right. And then Bev Clark Floss says, enjoyed this very much. Well, thank you, Bev. That's very nice. As did we. All right. Anybody else, if you make any comments here, or if you just listen to the podcast, send us a little comment over to podcast@vocommongood.com. We'd love to hear from. Is that good for the day?
It's great.
Over and out. All right, friends. We'll see you. We'll talk to you on Monday, and get on our email list if you're not on there yet, and don't miss that donate button when you do. All right.
Bye, everybody.